we're back with Unit 2, Matter and Energy. Just struggling over here, but it's okay. But, we're back with Unit 2, Matter and Energy. This video is long overdue. This was supposed to like 2 or 3 weeks ago, but, you know. Look at me go. Such good time management skills I have. Let's get started. So, the first lesson. Now, what is matter? Matter is anything that has mass and takes up shape, takes up space. Matter cannot be created or destroyed, but it can change form. Yeah, I guess that's it. And then there's 2 types of observations. So when you're doing like some kind of experiment, you're gonna have to document observations, right? So what are the 2 different types of observations that you can document? You can document qualitative observations. You can also document quantitative observations. So what's the difference? Qualitative observations are describe the characteristics of what is being observed, right? So it's color, flavor, texture, things you can describe using your 5 senses. So like this drink tastes like mango, you know? The texture is I don't know. It's fucking into liquid. I don't know what to tell you, right? So that's what qualitative is, and the quantitative is are observations that are precise and have a numerical figure. So, like pretty much a measurement. Like, oh, this this can is filled with 16 fluid ounces of Monster. Like that's quantitative because it has a number 16 and then like a measurement, fluid ounces, and 473 milliliters. Interesting. Yeah. Okay. So what properties can you observe when you are looking at you're looking at an object? Every object has physical properties which you can be observed without the breaking of bonds. Pretty much the sample remains the same before and after the observation. So density, color, order, odor, melting point, and boiling point. You don't have to break any bonds to observe those things. You can observe them with your senses. Yeah. And then what's a physical change? So it's when you change a substance without changing it chemically, without changing the bonds. So when you boil water, it goes from a liquid to a gas, but it's still water. It's still H2O. That's what a physical change is. The actual chemical composition of said thing remains the same, just maybe how it looks, change in size, shape, or state. Those things change. And then a chemical property, which is, unlike a physical property, you observe the reactions, which is the breaking and forming of bonds. So, pretty much you see how this substance reacts with another one. So, pretty sure they said, so iron to form rust because they're changing the actual, iron from iron to iron oxide, I believe. I could be wrong. I don't know. It's been like long since I took chemistry. So, so you're actually having a chemical reaction. So that's a chemical property that iron can rust. What's a chemical change? You are breaking or forming bonds to create a new substance, right? New substance is formed. So hydrolysis, it is the breaking of water, H2O, to create hydrogen and to create oxygen, right? So that's hydrolysis because you're changing water into 2 separate different substances. And then these are the categories of matter. You can kind of demonstrate them as this flow chart, I believe that's what they're called. Could be wrong. So so when you have matter, you can have either a pure substance or a mixture. So what are the different types of mixtures? The first type is a homogeneous mixture, right? So you cannot see the different parts. They're all uniform, and there's no really like fixed ratio, which is right. So homogeneous pretty much means the actual thing is uniform throughout. Like this monster, I'm just gonna keep going back to this monster because I have it right in front of me. It's a homogeneous mixture because if I were to pour this in a cup, it would all look the same. You won't be able to tell the difference between the water and the sodium citrate, whatever the fuck that is, within. I should not be cursing, whatever. But you won't be able to tell the difference between. You won't be able to differentiate them because it all looks the same. Then you have a heterogeneous mixture, which you can see the different parts and it's not uniform. Pretty much you can take apart the different parts. Like in sand, you can see each different particle. In salad dressing, you can tell the difference from I don't know, I don't eat salad. Or a salad is a type of mixture. It's a heterogeneous mixture because you can tell lettuce apart from tomatoes, apart from, I don't know, what the fuck do you put in salad? I don't know, salad, whatever. And then, how do you separate mixtures? You can separate mixtures physically because there is no chemical bonds, right? So there are different ways of separating mixtures. One way is filtration. It is mostly used when separating heterogeneous mixtures, and it is used to separate a solid from a liquid, right? So pretty much you use filter paper to catch larger particles. So I'm trying to think. Filtration, maybe you have I don't know, some fucking, can't think of anything right now. Sand and water. So you would put the mixture of sand and water through a filter paper, which it would cause the water to go through the filter paper while the sand remains, on top of the filter paper. So you separated the water from the sand. Does sand dissolve in water? I don't know. Who cares? Not important. And then you can have evaporation, which is used for homogeneous mixtures, and it's also used to separate solids from liquids. So pretty much you evaporate the liquid, and the solids left behind. An example of this is salt water. If you take a thing of salt water, you won't be able to see the salt. It just looks like salt water, right? But then you can evaporate the salt water. The water would go evaporate. Wow, that's amazing English right there. But the water would evaporate, and then you were just left around with the salt. So you're separating the salt from the water. And then distillation is used with homogeneous mixtures of different liquids, right? And you separate them by boiling point. So alcohol and water. So let's say you have a mixture of alcohol and water. Those two things had different boiling points. So whatever has a lower boiling point, you would boil that away first, and then you would have whatever has a higher boiling point left with whatever the lower boiling point, all evaporated and shit, And then chromatography, which actually I haven't really seen chromatography being tested on too often, but it's still good to know, I guess. This is used for the separation of homogeneous mixtures, and it's used by diffusion on polarity and molecule size. So the most common thing of chromatography I can think of is usually with the one I can think of is with markers, because let's say you have a black Sharpie or a black Crayola marker. It's a mixture of different types of ink, right? So you can use chromatography to see the different types of ink. I'm pretty sure there's some red in there might be some blue in there, I don't know. I haven't tried it. That's why I did try it, but it was years ago. I don't remember that, whatever. And then elements, which is also a type of matter. It's a pure substance. Elements are made out of a single atom, and they cannot be broken down at all. So if you have an iron bar, it's just pure iron. You can't break that down because it's literally just iron. You can't break down iron into smaller things. And then another pure substance is a compound, which is with two different elements chemically combined, and it can be broken down and separated, but you have to do it chemically. It can't be broken down by a physical means. So H2O, the hydrogen and the oxygen are chemically combined to create the compound H2O, water. You can't separate it using physical means, but you can separate it chemically. What are diatomic elements? Diatomic elements are elements that exist bonded to itself, right? So you can remember the diatomic elements using Brinkelhoff. Or another one is have no fear of cold ice beer. Those are two different ways that I remember the diatomics. So yeah, bromine. Bromine always comes as Br2, hydrogen H2, oxygen O2, nitrogen N2, chlorine Cl2, iodine I2, and fluorine F2. Pretty sure it's fluorine. Hold on, let me check actually real quick. Yeah, fluorine. Just making sure. Okay, and then this is just like the concept map, but let's go through it, you know? So you have matter, which you can be separated into a pure substance, which there's two different types of matter, a pure substance and a mixture, right? And then you can change between the two using physical changes. So you can take sugar, glucose, which is a pure substance, and make it into a mixture by mixing it with water. So that's a physical change. So pure substance, you have two different types of pure substances. You can have an element, and you can have a compound. An element is a pure substance that cannot be broken down, while a compound is a chemical combination of two or more elements, and you can switch between the two using a chemical change. So you can take an element, iron, right, and you can make it a compound, iron oxide, by chemically bonding it with the oxygen, which is a chemical change. Or you can use burning, that's also an example. I didn't really put an example of oops. And then a compound example is water, and then an element example is hydrogen gas. And also, why the fuck do I sound like a dying 50-year-old? Oh god. Okay. Now, a mixture. What is a mixture? It's a physical combination of two or more substances. So you can have a homogeneous mixture and a heterogeneous mixture. A homogeneous mixture, this is just, I'm going through this quickly since I already said this, but a homogeneous mixture is a combination of two or more substances that are uniform. They look the same throughout. While a heterogeneous mixture is of two or more substances that are different. You can tell the different parts from each other. So a homogeneous mixture could be Kool-Aid, it could be Monster, it could be salt water, right? A heterogeneous mixture, salad dressing, sand, salad itself. Why do I keep talking about salad? I'm actually kind of hungry right now. Whatever. Anyways, metals. Right, so this is, so this is, on the Google Classroom, I have the reference table posted for chemistry, or chemistry regions. I actually do also have it on, I'm pretty sure I also have the AP Chem one on there too, I don't remember though. But pretty much, you have this beautiful periodic table. Well, it doesn't come with all those notes, but so all the metals on the periodic table, they are on the left side of the staircase, right? So what that means is, don't have enough hands for this, but is there a photo of it? I'm gonna hope there's a photo, please. Okay, there's not, but if you're looking at it, right? There's like a black dark line, right? Like let's say you have aluminum, Al, element number 13. Then next to it you have Si, silicon, element number 14. There's like a black bar, and then it kind of goes on in the shape of a staircase, right? So everything on the left of that is a metal. That's pretty much what that's trying to say, right? And pretty much one thing you want to be able to know is that when you move further to the left or further down on the periodic table, there is more metallic character. But what are the metallic characters? What are the characteristics of a metal? They're good conductors of heat and electricity, right? They're malleable, which means you can shape them however you need. They're ductile, which means you can kind of like pull them into wires. Like I don't know how to explain it, but I mean most wires, like electrical wires, are made out of metal because they're ductile. I'm pretty sure I'm pronouncing that correctly, right? Ductile, right? They're lustrous, they're shiny. Most metals are pretty fucking shiny, right? And then an example is gold. Who doesn't love gold, right? And then a non-metal is on that same staircase which I described before. They're actually, you know what? Let me just like pull up the actual thing. Chemistry. much, this is the staircase I'm talking about. Next to the, what's that element again? Boron. Boron, aluminum, silicon. Nope, forgot that, whatever. This is the staircase I'm talking about. So you have an idea. Okay, well, non-metals. Woo! Okay, they're on the right side of the staircase, so carbon, nitrogen, oxygen, fluorine, neon, phosphorus, yeah, whatever, right? And then when you move to the right and more up, there's more non-metallic characteristics. So what are the non-metallic characteristics? They have low boiling points, they're very brittle, they're dull, and they're good insulators. So sulfur is a good example of a non-metal. And then metalloids are semi-metals, right? These are, on the staircase, they're found, like, pretty much touching the staircase, right? And they are both, they have characteristics of both metals and non-metals, which is why they're called metalloids. They're a mix of both, pretty much, right? And they are good semiconductors and transistors. An example of it is silicon, but there's also boron. There's silicon, I already said that. There's germanium, there's arsenic, there's antimony. I definitely did not pronounce that right, but that's one. There is also T, which is number 52, and AT, 85, which is, I don't know how to pronounce half of these. Whatever, but those are also important to know, but, because, you know, yeah. And then, if you did print out the chemistry reference table, I would suggest kind of coloring and coding it like this. All the blues are metals, all the yellows are non-metals, and the metalloids are pink. That's what I would recommend doing. I mean, obviously, this is a bit outdated because it doesn't have, like, all the other new elements. Like, it doesn't have fucking, whatever, right? But I would recommend, color coding it because it makes it easier, but yeah, you don't have to. You don't have to listen to me. Whatever. Okay. So states of matter, right? There's solid, liquids, and gas. This is pretty well known, but why are there different states of matter, right? And it depends on two factors. So pretty much you have heat or kinetic energy, or temperature pretty much, which is the movement between particles. How fast are particles moving in a substance? Right. It can also be the force between the molecules, right? So opposite charges attract. So usually very non-polar substances, they're usually gases because they don't have any opposite charges. I'm pretty sure. I'm gonna hope that's correct. I'm not just spewing BS. But whatever. So these are the different states of matter. A solid, very tightly bonded with each other, very close. There's pretty much no, well, there's a little bit of movement, that's why there's no, but they're very tightly bonded. Liquid, they're less tightly bonded, but they're still somewhat, is bonded the right word? I don't know if bonded is the right word. I don't think bonded is the right word. It's not. But the particles are more tightly packed. That's what I was looking for. Tightly packed in a solid. They're less tightly packed in liquid, so they're still able to move past each other. And a gas, they're not packed at all. They're like all over the fucking place. They can do whatever the fuck they want, right? Plasma is not really that important, but it's cool. It's just free-flowing electrons and protons, pretty much. But it's pretty fucking cool in my opinion, but it's not really that important for reagents, right? So as you increase kinetic energy, you go from solid to a liquid to a gas to a plasma. To a plasma? I don't know. Whatever. And the reason is because the strength between the molecules decreases, which means they're more likely to separate and move past each other. Right, so solids, what are solids pretty much? They have a definite shape and volume. They are tightly packed, so they can't slide past each other easily. And you can't push them together. So this, I'm trying to think, what's a good solid? Here, this crystal that I have, this amethyst crystal, I don't know if you can see it, but it's a solid. It's tightly packed. There's no moving, and I can't really press this onto itself. I'm gonna that was expensive. Let's not talk about that though. What are liquids? They have an indefinite shape, but they have a definite volume, right? So the liquid inside this monster, like, if I were to spill this, it would change shape, right? But it would still be the same how many fluid ounces there is left in there, because I did drink some of it, right? They're close together, but they can still slide past each other, right? They're incomprehensible, so you can't really put pressure on them. You can't really make it tighter, if that makes sense. I don't know if that makes sense. Not important. Whatever. Gases, they are in an indefinite shape in an indefinite volume, right? So you put a gas in a container, it's gonna fill the entire container. You move it in a different container, it's gonna fill that entire container. So no definite shape, no definite volume, right? And they're far apart from each other, right? So you're gonna have a gas particle here, and then another one's over here, another one's over there, you know. And they're highly compressible, so you can put pressure on them, and the particles will come closer together. And they're highly disordered; they're moving all over the goddamn place, right? And then a plasma, they are a group of highly charged particles, so electrons and ions, because they have very high, they're electrically charged, right? And they usually carry electric current, so a lot of them, lightning, fire, taser guns, those, because they are composed of electric, high energy charged particles, they are considered plasma. And I think that's it. Ooh, wow, we're done with Unit 2. Look at us go. Doing great. Anyways, have a good day. Don't die. Oh, I forgot that was there. Oh my god, when I actually did streaming, that was a while ago. But yeah, yeah, if you have any questions, ask me. Is there anything else I want to say? In the description, if I remember, I should have the link to the Google Classroom. So if you're not in there, join it. Yeah. Have a good day.